Now we're going to introduce hypothesis tests where we're comparing multiple samples. And the most common place this shows up for a data scientist is what's called A/B testing. So, often we're interested in testing whether two samples look like random draws from the same underlying distribution. When might we be interested in this? We're often interested in testing whether two samples look like random draws from the same underlying distribution. This could be the case if we're trying to decide whether or not to redesign a web page, redesign a product, release a new product. In all of these cases, when we think in the context of hypothesis testing, before we even do a test, we have to have a default action. Typically, without new data, we don't usually make changes. So we wouldn't typically release a new product or change web pages, etc., without some data that convinces us that a change is needed. So typically the default action is, there's nothing special about this new product or this new version of the web page. And then we can put this to a test by actually getting two different samples and seeing whether or not via statistical analysis, the difference between those samples could be explained just by chance. Or if there's something more significant going on, meaning they came from different underlying distributions. So when you try to answer this question by performing a statistical test, we'll call it A/B testing in this class. Technically, it's A/B hypothesis testing. So where's a place that we might apply this? I'm going to use data we've already looked at, just so we're familiar with the data to start. We had the data of babies and mothers, and one of the pieces of info we looked at was the birth weight of babies, depending on whether or not the mother smoked. So here is a box plot, as well as overlaid histograms that we created when we were doing our data visualization. And we can see that the birth weights, at least the median birth weights and the distributions themselves, are shifted. The median birth weights are lower for babies whose mother smoked, but not, hugely lower. And so it's unclear whether or not this was just some random variation in the samples and, could have just happened by chance, or if this is really indicating that the underlying distribution of baby weights in the population is really different for babies whose mother smoked versus those who didn't. So if you think of the A versus the B in this scenario, we could let A be the birth weights of babies of mothers who didn't smoke, and B be the birth weights of babies of mothers who did smoke. And ask the question, could the underlying distributions of birth weights be the same for both groups? And the difference we see in these samples just be due to random chance. That's the context that we will enter this hypothesis test with. Just to give you a visual of how this could happen, let's actually go back to the website that we explored when we were looking at the central limit theorem and visualize taking two random samples from the same distribution. So we're on the onlinestatbook.com sampling distribution webpage, and we've been here before, but now I want us to visit it from the context of imagining, if we had some underlying population distribution of the weights of babies, and if this really wasn't different between babies whose mothers smoked versus those who didn't, we'll notice how we could get two samples. So let's do samples, we can do 25, just the full big thing here. Let's do two samples of size 25, and we're going to calculate the means in both. So here's one such sample, and I'm going to get a sample mean here. Okay, there's one sample mean. Now I get a different sample, and so my new sample is going to look different, and it's going to have a different sample mean. Right? So here I can see it's a slightly lower mean in this sample versus this sample. But it doesn't mean that these came from different distributions. These actually came, we watched it. These samples came from the same distribution, and just by chance, one of the sample means was slightly lower than the other. So this is really what we're trying to test. And so our null is not about the specific shape of the population distribution. We actually don't know. It could be that the weights of babies looks like this. It could be something totally different. We don't know. And we're not concerned actually with the shape of it. Our null is just that whatever the distribution is, the two samples we got came from that same distribution. And so the differences that we saw in their sample means was just due to random variation. Let's pop over to the Jupyter Notebook to also start setting this up in code. So I am in the hypothesis test folder now in the A/B testing notebook. And I'm just going to load the data and just plot the same plots I was showing on the slides where, oh, that's just looking at the number that we had in both groups. And then I can plot the distributions, the overlap distributions here where I see the shift. It's a little bit easier to visualize it using these box plot. So let's do that instead. Like I said, so I see that I have a shifted lower distribution here. The median's lower here than it is here, but could that have just happened via chance? Okay, so how do I set this up in the context of a hypothesis test? Our null is going to be that in the population, the distribution of birth weights of babies is the same for mothers who don't smoke as for mothers who do. So the observed difference that we see in the sample is just due to random chance. For the alternative hypothesis, let's actually pick a direction here. So we'll say no, the alternative is that in the population, the babies of the mothers who smoke have a lower birth weight on average than the babies of the non-smokers. Now, to actually conduct this hypothesis test, we're going to pop back over to the slides to set up what test statistic we'll need to use. So let's summarize this null and alternative hypothesis. And I'm going to point out that in these cases, I have an observed sample of weights with two different categories, but I don't know the underlying population distribution. So that's a difference in this test and what we've previously been doing with hypothesis tests. With a previous hypothesis test, I've either known the underlying population distribution or I've made some hypothesis about it. Here, I'm not making any assumptions about it, and I don't need to. In terms of the actual shape of the distribution or any of its parameters, the only assumption I'm making or the only hypothesis I'm testing is whether these two samples came from the same distribution. But what that distribution is remains to be unknown. So, what test statistic will help us in determining which of these two hypotheses is more consistent with the data? Because I have a direction associated with my alternative hypothesis, I'm looking for weighing less here. I'm not going to be using an absolute value in my statistic. I am going to want some way of measuring the difference between the distributions. Because these are continuous random variables, that the birth weights can take on all types of different values, I wouldn't do something like TBD because I don't have, a discrete number of categories. So instead, I need to take some kind of summary statistic from each distribution and compare that. So great choices are the mean or the median. And we could look, for example, at the difference in the means or the difference in the medians. Either of those would be great test statistics. So I am going to look, just for the sake of this, we're just going to choose the mean. And if I let my group A be non-smokers and my group B are the smokers, my statistic is going to be the difference between the average weights. And I could choose either mean A minus mean B or the other way around. I'm going to do group B average minus group A average. So given that's what I've chosen for my test statistic, what values of the statistic will favor the alternative? That's going to be important because that's where I'm going to need to look in my distribution of the test statistic. It tells me which direction of the tail I'll be looking. Okay, well, let's see. The alternative is that the birth weight of the babies whose mother smoked is smaller. And so if group B is the babies whose mother smoked, if I take their weight minus the group A, I would expect negative values of that will favor the alternative. That's just the way I've set it up. Because that would mean that my group B average is less than my group A average. You could set it up the other way, and then you'll just be looking at the other tail in your test statistic distribution. All right, so given this, now I want to go simulate. So let's put that here. I want to simulate my test statistic under the null hypothesis. So this is where we're going to need some new strategies because we haven't figured out yet how we could simulate this situation here such that we could then calculate a difference between the weights or the mean weights. And so the new tool we're going to use is actually this idea of what's called a permutation. So if we assume that we're in the world of the null hypothesis, where the distributions of the birth weights of the babies in the two groups are the same, then if we took our data, right now it's for each baby weight here, it's matching it with either a non-smoking mother or a smoking mother. We could take the weight, keep the weights the same, and just rearrange the labels. So do a permutation of whether the mother was a smoker or not. So in other words, I'm shuffling the group labels, keeping the baby weights the same. Why is that going to work? Well, if we really lived in the world of where the null population were true, then all rearrangements of the labels are going to be equally likely, right? Because they all came from the same distribution. So whether or not they were labeled smoker versus non-smoker, wouldn't make a difference. We're shuffling them or permuting them so that we keep the same number of smokers and non-smokers that we had in the original data set. That's important. We don't want to change that piece. And that's why we're going to do this idea of a permutation. So this has a formal name. When you do a permutation like this as part of a hypothesis test, it's actually called a permutation test. So this A/B test is one example of what's called a permutation test. And in order to do a permutation test, you need 2 or more samples of data, and your null is that the samples are random draws from the same underlying distribution. To create the permutations, you shuffle the values in the label column, keep the other columns fixed, and then you can calculate the test statistic for the shuffled data. That's going to constitute one simulation of your test statistic. You'll repeat that a bunch of times and then plot your empirical distribution of the test statistic. So let's go over to the notebook to see this in action. So in the notebook, we're actually going to create a function right now that will calculate the difference in means for 2 different categories. I'm leaving this function fairly generic so that we can use it in future examples as well, but it's going to take in a data frame. It'll take a column label of a numerical variable, in this case, the weights of the babies, and a column label for now of a Boolean variable, in this case, whether or not the mothers smoked, and it's going to return the difference of the means. And I have a particular order. It's going to take the true minus the false, because that's the way we've set up our test statistic. So this is just giving me a data frame with the 2 relevant columns. This is grouping each category label, taking the mean, right, and then spitting out the difference in the means. So if you want to see more steps to this, you can print more of these, but I just print this part just so you get a sense of the group by. And then let's run this here. And so here's the grouped function output, and we can see this is in the original data set. This was the average birth weight for babies whose mothers didn't smoke versus those who did. And this test statistic we're interested in was actually this true minus the false, so this negative 9.2. And that's what it's calculating here in the actual observed test statistic. Now, in order to simulate this test statistic for lots of different scenarios, we need to actually play around with how we do permutations here, or shuffling. So I'm going to actually do it with a simpler data set first, and we're just going to play around with these functions, and then we'll implement it in our full data set. But just to make this easy, imagine I just had two different groups. I either label them label 1 or label 2, and then there's some quantitative descriptor or some quantitative feature I'm measuring in each group. So maybe it's ages here. And maybe I'm going to look at the difference in the average ages or the difference in the median ages. Okay. Before I worry about calculating the actual statistic for each group, I want to practice how I can shuffle around these labels. So I am going to just first notice what happens if I just call the .sample function on a data frame. And here, it's going to just sample one of the rows randomly. And I run it again, I'm getting a different row. The default is without replacement, so if I sample 3, it's going to give me 3 here. If I would like to sample the entire data frame again, just randomly, I can put frac equals 1. That's telling me the fraction of the original data set I want, and here's a random sampling of that data frame. So we're going to use this to our advantage. And now we're basically going to just add a new column to this data frame with shuffled labels. So if you notice, I'm calling shuffled labels, and I'm doing this exact thing we had here. You don't have to have replace this false because that's actually the default, but I'm just putting it in there to be extra thorough. And so you can see now, here's an example of my original data frame right here, and now my shuffled labels. And I could do it again, and I'm going to get a different shuffling. The way I use this now, so these are my different permutations. I'm just running it over and over. Now, if I wanted to calculate my new test statistic using these shuffled labels, I would go find all the label 1s and take, for example, their mean, and then all the label 2s and take their mean, and then take the difference. So that's what we're going to do in the context of our full baby weight data set. So that's what's happening in this function. And again, I'm creating it pretty generic so that we can use it in future examples. So I'm allowing us to have the option where maybe we'd be interested in the absolute difference. Maybe we'd be, in this case, we're not. We're having an actual difference without taking the absolute value, but this just gives me some more flexibility. So I'm shuffling the labels, and then I am putting them back into adding them back into my original data frame. And then I'm plugging that into the function I wrote above, right? So that I get the new mean out using the shuffled label instead. So let's actually see what happens. I'm going to just do print example true here so you can see exactly what will happen. I needed to actually run that function, but now we can run it here. Okay, so here's my original data frame here. Here's now the shuffled labels. And so when we're creating our new grouping, I'm using the shuffled labels, and then saying for all the false shuffled labels, what are the average birth weights? And all the true, what's the average birth weights? And then I'm taking the true minus the false. So you can see in that round, it was very tiny, right? But we could do it again. I'm going to get a different. There I had 0.217. I'm going to do it again. And so these are showing me all the possible values of the test statistic I could expect, assuming the null hypothesis is true. So we repeat this process. I'm going to do it for 10,000 simulations and then plot the histogram. And I'm going to put the actual observed test statistic on the histogram as well, just so we can visualize. Aha, let me pause this first because I've been printing out in this function up above just so we had a view of what was happening, but we really don't want to print that out each time. So I'm going to comment this out, and then that will save us a lot of unnecessary, here we go, unnecessary pain. And right now I'm going to have one simulated difference. Okay, there we go. That looks good. So now it's running it, and we're going to print out or visualize our histogram in just a minute. Here's our result, as well as our observed test statistic on this distribution. And so again, if you recall, more negative values were going to be in favor of the alternative in this situation. So I can see, first of all, my observed test statistic is wildly in the tail of what I would expect, which is making my null hypothesis look pretty unlikely. To actually calculate my p-value, I'm going to calculate the number of my simulations where I ended up with a value that was either this -9 that we had for our observed test statistic or smaller. So to write that here, or to code it, I'm counting how many of the simulated statistics were less than or equal to the observed difference. I'm calling it _AB, just because that's actually how I saved it up here for the AB test. So see the number that are less than the observed difference out of the total, so out of the 10,000. And when we run that, we get 0. We saw 0 out of 10,000. So again, this doesn't mean my theoretical p-value is 0. It means that it's smaller than 1 in 10,000. So it's definitely less than typical cutoff values that we would use for our significance level of 0.01 or 0.05. Either of those are valid p-value cutoffs, and this is definitely much smaller. So let's go back to our slides for a conclusion. So to summarize what we did in this process is we concluded from our test that because our empirical p-value was less than the significance level, and I should have put the significance level here earlier because we need to pick that before you do the test, but a gold standard, especially for data that involves health impacts related to humans, is to at least use a significance level of 1%. You could do something even smaller, but 1%'s reasonable here. So we reject the null and we say the data is consistent with the alternative. So what does that mean? So this means we do have data that makes our null look pretty ridiculous. We have reason to believe that it's likely in the full population, the birth weights of mothers whose babies smoke do weigh less than those whose mothers do not. However, by no means are we able to make causal claims just alone from this statistical test. Because I can't tell in this situation, we didn't randomly assign mothers to smoke or not to smoke. So when you do what's called a randomized control trial, which we're going to cover in the next video, you can make causal conclusions at the end of your statistical test. But when you're using observational data like this, you can't make causal conclusions without being very careful and doing much further analysis, because you need to take into account what are called confounding variables, other things that may be contributing to what we're seeing in this test. So again, this is an important conclusion. We did find that these two were associated. We've concluded that yes, there is some association between the birth weights of babies whose mothers smoke and those who do not, and we have a specific direction. We know which one's less, but we cannot say that this was causal. So in the next video, we'll look at how we can set up randomized control trials to actually make causal claims.